Good morning, everyone. Welcome back. All right, so for today's class, we are actually going to officially move into Unit 3. We are going to start learning how to translate written English into algebraic expressions and algebraic equations. This includes starting to work on word problems, which I know is definitely something that we all love to do, right? Yes. And if not, that's okay. I would imagine that once we're done with these kinds of discussions and kind of showcasing the steps to move through it, I feel like you're going to have a lot more confidence in solving these word problems, and you might actually really enjoy them and look at them as like little puzzles, right? You ever put a puzzle together and you're like, yes, I did that. That was so great. I want the word problems to kind of feel like that, like a brain teaser that you're solving. And then you could say, yes, I did that. Success. Okay? All right, let's take a look at our notes and see how we do. Changing application problems into equations and then solving them. So the following chart you're going to use to help you essentially set up word problems. We're going to focus on word for word interpretation. That's why it's really important for you to be familiar with the phrases that indicate specific operations. So, having said that, if we are referring to addition in our statement, our written English statement, then we'll see key phrases like more than, increased by, added to, some of this and that, right? Like some of this first piece and the second piece. So some of implies you're adding the two pieces together. Plus or total. The really nice thing with addition is that order does not matter. Recall the commutative property. 2 plus 5 is definitely the same as 5 plus 2. So with addition, we're not too worried about the order of your terms, just so long as you're using word for word interpretation. When we look at subtraction, we have the phrase less than, decreased by, subtracted from, difference between the first term and the second term, or difference between the first expression and the second expression, and then minus. I will tell you that with subtraction, you really have to be careful because order matters. It definitely matters. I mean, think about it. 10 minus 2 is not the same as 2 minus 10. So subtraction is not commutative. So we want to be really, really careful with that. The other thing that we need to be careful of is these two phrases, less than and subtracted from. Notice that in parentheses it says reverse the order. I'll show you exactly what that means with an example statement to illustrate what it looks like if you were to reverse the order. So hold on to that for right now. We'll see that in a minute. Next, if we're looking at multiplication, you have clue words like times, or phrase product of the first expression and the second expression, product, right? You're multiplying. The word of by itself implies multiplication. Usually you'll see of with percentages or with fractions, right? So think about if I said, what is 25% of 100? Well, if you heard the phrase 25% of 100, you're going to say, okay, 0.25 times 100. That of implies multiplication, 25% of 100, right? I turned 25% into a decimal. Similarly, what if we had a fourth of 100 or 1/4 of 100? So we could think of it as 1/4, right? Our fraction 1/4. And then of 100, of implies multiplication, so we end up with the same expression. I wanted to kind of show you that back and forth action there. So of implies multiplication. We also have multiplied by, and then we could get fancy with it. Twice, thrice, yeah, I know. You're probably thinking, wow, great. But that means 2 times that value, 3 times that value, etc. Okay, we can get fancy with it. Typically, you'll see like 5 times a number instead of, whatever it would be for 5 times. With multiplication, we know that the order doesn't matter. We know that 3 times 2 is the same as 2 times 3. We know that 1 times 2 times 3 is the same as 3 times 2 times 1, right? We've had these discussions before. So we're not too focused on the order here. I will tell you though, if you had to decide on the order between a quantity like 5 and then an unknown like a variable, you should always put the quantity in front of the variable, okay? You shouldn't write m5, that's weird. It should be 5m. So coefficient, variable. Hopefully that makes sense. And last one we're going to look at is division. So the clue phrases that indicate division are over, like 10 over 2, right? 10 over 2, duh, we say that all the time. We have the quotient of, this one we don't say all the time. So the quotient of 10 and 2. Notice that the 10 represents the numerator, and that's essentially the first blank. And then the 2 represents the denominator, and that's the second blank. So this and is essentially separating the numerator and the denominator. Figure, why don't we write it that way? So the quotient of the numerator and denominator. So it could be a single value. It could be an expression in either of these locations. So we have to read it very carefully. And then divided by, like 10 divided by 2, right? So essentially we are familiar with the first and the third, but not so much the second. But I want us to be familiar with those, and I want us to be comfortable with this idea for these phrases for division. As a reminder, order definitely matters again. We know that 10 divided by 2 is not the same as 2 divided by 10. Those are totally different quantities. So we want to be careful when we do that. Perfect. Next, any unknown quantity can be represented by the variable of your choice. I want you all to stop using x every time. Don't do it. If we're talking about the length and we're solving for the length, use L. If we're trying to solve for the width, use W, okay? If in our word problem we're talking about Ashanti, I'm going to use A. So we need to get out of using X for all of our unknowns. I have found that 9 times out of 10, when students use the variable pertaining to what they're solving for, they'll get it correct because they know what they're looking for. If you use X and you finish solving and it says X is like whatever the value is, X is 5, I've had students say, wait, what was X again? What was the value of that? And then get thrown off. If you use the variable that pertains to that particular value, length L, width W, height H, you're going to be in such better shape, okay? So please heed that advice. You don't have to, but I highly recommend it. Okay, we have many letters. Use something other than X, okay? Okay. Any word that represents the solution like is, are, were, was, yields, becomes, results in, all that kind of stuff, they all mean equals, which is pretty cool. Okay, so as promised, I wanted to give you an expression, or excuse me, an equation in this case, that uses the phrase less than, so you know what I'm talking about. So notice here we have 2 less than a number is 17. So if I wrote it directly above, I'd say, okay, well, 2. I know that less than is subtract. A number, well, I don't really know what that number is, so I'm just going to call it B. I know the word is means equals, and then I have 17. So notice how I've literally just done word for word interpretation. Now, the fancy thing about less than is that these terms, the 2 and the B, they'll end up getting flipped, okay? So we have to think we're subtracting this one and this one, which means they need to flip places. So 2 less than a number of 17 is actually written B minus 2 is equal to 17. This is the same idea when we talk about subtracted from, okay? I could have said 2 subtracted from a number. It would look like B minus 2, okay? So be very careful with that. Hopefully that was clear, and it's just those two. If you see less than or subtracted from, let's think, ooh, there's an extra little step here that we need to be careful of, okay? Last, we need to consider the steps for setting up and solving word problems. Lots of times I see students forget step number 1, and that's prior to our conversation, obviously. So what I'd like you to do is to, again, heed my advice. Your step number 1 is you're going to establish the relationship. You have to figure out how these unknowns relate to each other. If there's more than one known, you have to say, well, how do they relate? Okay? You establish that by writing out the relationship first. After you have the relationship set up, you then go ahead and say, okay, well then let's write the equation given by the word problem. We have to identify what the word problem is saying and write that equation. We're going to solve the equation, and of course, it's not enough to just solve it. It's not enough to just say m equals 5. You want to answer the question being asked and label this answer. You need to be able to demonstrate that you know what it is you're solving for, and you can essentially label it. By labeling it, it proves that you understand. Good morning, Alexis. No biggie. Okay, let's turn the page. Typically, we would go round robin in class, and everybody would get an opportunity to do these. So as we move through this, I'll give you guys time to write in the chat. But for now, I'll start us off. So our first statement is a number increased by 15 is 38. So the first letter of my first name is R. So a number, I don't know what that number is. I'm just going to call it R. Increased by, we know increased by refers to addition. Then I have the number 15. Then is implies equals. And then we have 38. Do you see how we moved left to right, word for word interpretation? We know with increased by, there is no need to flip the order of terms. So we're all set here. Number 2, 3 times a number decreased by 26 is 88. Okay, again, word for word, I'm going to use a different variable this time. So 3 times a number, we can call that 3a. So 3 times the number, we don't know what that number is. Decreased by, we know decreased by implies subtraction. 26 is, that is means equals 88. Excellent, Claire. You're absolutely correct. Notice here that decreased by is not one of the fancy expressions where you'll end up switching the order of the terms. You don't have to do that with decreased by. Excellent. As I move through these, you all feel free to write your expressions or equations, in the chat so that I can see that you're answering these before we even get there. So give this a shot and move through this page and just go crazy. Throw in all your answers in the chat so I can see what's going on. And I'll move nice and slow so you have time to do that. Number 3, the sum of a number and 11 is 49. Well, the sum of, okay, that definitely means that we're adding 2 things, right? Notice the word and here. So the sum of this first piece and this second piece, and then we have that equals 49, right? So the sum of 2 things, we're going to add a number. Let's use C in this case, and 11. So we have C plus 11 equals 49. Excellent, Hannah. Excellent, excellent, excellent. Number 4. Number 4, yes, Kayla, beautiful work. Number 4, the difference between twice a number and 50 is the number more than 12. No, Hannah, you did awesome. You're doing awesome. The difference between twice a number and 50 is the number more than 12. Okay, so we're going to think about this. First off, difference between, we know that that implies subtraction. We know that there's an equals here, right? So I'm going to put an equals. We know that this information comes after the equals, and we see that there's a more than. So we've got a couple things going on here. We have to focus on the left side of the equation, and then we have to focus on the right-hand side of the equation. So the difference between, so we're subtracting 2 things. We're subtracting twice a number and 50. Do you see how the and says, here's the first expression, here's the second that we're going to be subtracting? So twice a number, I'll say 2f, and then 50. Excellent, Kayla. So we have 2f minus 50. The difference between twice a number and 50 is, and then Kayla finished this off. She said, well, the number more than 12, that's just going to be the variable again, more than 12. Excellent work. So that is perfect, Kayla. Notice that Kayla also says we have to use the same variable because it doesn't say another variable or another number or a different number, right? Twice the number and 50, excuse me, the difference between twice the number and 50 is a number more than 12. So that value, that unknown, is the same variable. Good. Let's take a look at number 5. 12 less than 4 times a number is 107. Aha. We see here less than. Right away, that should be like ding, 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 ding. We should think back to the previous page and say, okay, here. So we have to flip the order of the terms. So first off, we know that we have 12. We know that less than is minus. And we know that 4 times a number is 4p, right? I'm just going to use p this time. So what we recognize here is that these expressions or these terms, they're going to have to swap positions because of this less than. Yes, Hannah, perfect. So we are going to, and Patrick, that's perfect. So we are going to take 4p, write it first, minus 12. We see the word is, which means equals, and we have 107. Yes, excellent work. 4p minus 12 equals 107. Or Hannah says 4z minus 12 equals 107. So I love it. I love your use of variables other than x. This is cool. This is fun. I like it. Let's take a look at number 6. 5 times a number subtracted from 75 is the number added to 15. Take a couple seconds, type that into the chat. Let's see what you get. Excellent, Doc. That is fantastic. So I want to break down for everyone what Doc just wrote. First off, he looked at this, okay, 5 times a number, and he used C. So 5 times a number. We know subtracted from means subtraction, obviously, but this is one of the fancy ones, where if you have your terms before and after because it's subtracted from, you actually have to flip the order of those terms. Yes, excellent, Hannah. Thank you, Kayla, for giving this a shot. So 5 times a number subtracted from 75. That implies 75 is the first term, and then you subtract 5c. So 75 minus 5c is the first half of the equation. Then we have equals, and then we have the number added to 15. Excellent work, Doc, Kayla, Hannah. Thank you so much for your contributions. That is exactly how we would break down that statement. I love this. Let's try 7 and 8 in the chat while you're waiting. So if you have 7 and you want to give this a shot, go ahead and do that as well. So for number 7, we have 3 times the sum of a number and 23 is 60. This one's kind of tricky. And then for number 8, the product of 6 and a number increased by 2 is 42. Let's see what you have in the chat. I have to say I am incredibly impressed with the answers you're providing in the chat. This is super fantastic, and it's not commonplace to see that kind of feedback. It's awesome. I am super, super, super impressed. So we have 3 times the sum of a number in 23. All of you realize that the sum of a number in 23 is an algebraic expression in and of itself. So I'm going to use L this time. So the sum of a number and 23, L plus 23, but notice we have 3 times that sum. So because we want 3 times that sum has to be packaged in parentheses with the 3 in front. Like I said, I am so impressed that that didn't stump any of you. That was so awesome. Then we have the word is, which is equals, and we have 60. I almost never see this kind of response immediately. So like I said, you are all doing amazing, amazing, amazing. For number 8, the product of 6 and a number. So the product of 6 and a number, we can use 6e. Let's do that because we haven't seen e yet. So the product of 6 and a number increased by 2 is 42. And perfect. I love it. I love it. You all threw that into the chat like it was a no big deal. That is fantastic. I'm very, very impressed. Beautiful, beautiful, beautiful work. All right. I'm going to turn the page so we can continue. Let's take a look at number 9. Now this one for sure has stumped students in the past. An amount increased by 12% is $58. This has certainly stumped students in the past. Give this your best shot. I would love to see what your interpretation is for number 9. Okay, for this particular problem for number 9, I'm seeing a lot of answers in the chat, and that's awesome. But we actually have to fix our responses to this. We essentially have to tweak our equations just a little bit, okay? What we have been thinking about doing was saying, okay, an amount. I don't know what that amount is, so let's call that B. Increase by, we know, means addition. 12%, we know that we're going to write 12% as 0.12, and then we wrote the word, or excuse me, we wrote equals to represent is, and then we have $58 here. Now there's actually one piece missing. When you take a percentage, you're taking a percentage of a value, correct? So when you hear the word of, you should think multiply. 12% of something. Logically speaking, wouldn't it make sense to take 12% of the value that you're purchasing to begin with? So in this case, we call B that amount. It could be a new, the new PS5 that's coming out. We can say that that represents the cost of the PS5. And then let's say there's a 12% tax somewhere. Ugh. But let's say there's a 12% tax. Wouldn't it be 12% of the cost of the PS5, and that's how you'd figure it out? By not including another variable next to the point 12, you're actually saying the cost of the item, we'll call it a PS5, the cost of the PS5 plus 12 pennies is 58 bucks. That cannot be, right? That cannot be. And obviously the PS5 is a bad example because there's no way it's 58 bucks. It's like $500. But anyways, we need another variable next to the percentage because without it, you're saying it's being increased by 12 pennies, by 12 cents. I'm going to show you a real world example so that this clicks. But if you go back to your notes, you need to have a variable here. It needs to be the variable plus 12% of the variable equals 58 bucks. So let's look at a real world example just to play around with this. So I'm hopeful that you all have your calculators handy because you may need them. Okay. So let's talk about buying winter boots. Okay. We know that it's starting to get cold here in Rochester, so we have to be thinking about winter, right? Unfortunately. So let's say that your winter boots cost, we'll say $150. And because we're in New York, let's say that there's an 8% tax. I want you to take a moment and in the chat, tell me how much those winter boots will cost. Remember, you got to pay for the boots and you have to pay for tax. So in the chat, real quick, tell me how much these boots are going to cost you when you bring them up to the cash register and you pay for them. Okay, so not only did you provide the answer in the chat, but I asked you, how did you get that? And you typed in your responses. So it's brilliant to be able to see exactly what you did. So looking at what Patrick and Noelia said, you first have to take the 8%, 0.08, and you're going to multiply it by the cost of the boots themselves to figure out what that tax is. So when you take 0.08 and you multiply it by 150, you know that this is $12, right? The tax itself is 12 bucks. But what you also know is that you can't just pay the tax for the winter boots, right? I mean, that would be amazing, but you can't do that. So what you notice is that you actually have to take the cost of the winter boots and add them to the tax. So in this case, we end up with a total of $162. Okay? Now, I want us to think really logically about what we did here. You took the cost of the item and you added to that 8% of the item, right? Of means times. So 8% of the item, and that's how you got your total. Well, what number 9 in our packet is describing is that what we don't know is the original cost of the winter boots. So instead of 150, I'm going to replace it with B and pretend that I don't know what that value is. But what I do know is the process won't change. So it's going to be the winter boots plus 8% of the winter boots. See how I replaced 150 with B? And that's equal to $162. I'm hopeful that by showing you a real-world example, it makes sense why we need another variable after that 0.12 in our example. We need to say we're taking the percentage of some sort of quantity. In this case, we're saying that we don't know the original cost, so it's the cost plus 8% of the cost is $162. Now, just as a side note, I want to actually solve it for you. So if we had B plus 0.08B is equal to 162, what I want you to consider is the coefficient of my first term. If I do not have a number written in front of my variable, I know that that is a 1. So then we have 1 plus 0.08. If you get freaked out by that kind of thing, don't overthink it. If you literally punched in 1 plus 0.08, you would get 1.08. A way to think about this is $1 plus 8 pennies, right? Or $1 plus 8 cents. That's going to be $1.08. So we combine like terms. If it were subtraction, it would be 1 minus 0.08, right? If it were subtraction, but in this case, it is addition. So we combine the two terms, and now we divide by 1.08 on both sides. When we take 162 and we divide by 1.08, guess what? We get the cost of the boots, $150. This is how you work through a problem where you don't know the original cost, but you know the result. Okay? This is the process. I really hope that I was able to drive this point home so that you will always get these kinds of problems correct. Moral of the story, when you're dealing with percentages in an algebraic equation, it should be percent and then variable. So percent variable. Always think of that there should be some sort of variable attached to that percentage if you don't know the original amount. Okay? Let's go back to our notes. Number 10, try this one. The cost of a pair of shoes after a sale of 40% is $35.50. Let's see what you get. All right, so the cost of a pair of shoes, well, we don't know what it is, and I'm going to use fancy S because if I use a regular S, it looks like a 5, and then it's terrible. After a sale, this whole concept here, I want you to think of when you have a sale, when you have a discount, things like that, you're subtracting the value. Patrick, that's okay. So the cost of a pair of shoes after a sale of 40%. So 40% can be 0.4 or 0.40. And then, of course, we need the cost of the pair of shoes. So the cost of the pair of shoes minus 40% of the pair of shoes is $35.50. Excellent work, everyone. Excellent, excellent work. As a reminder, the coefficient here is a 1, so this is 1s minus 0.40s. Think of it logically. If originally you were responsible for 100% of the cost of the shoes, and then they're like, no, we'll just take, we'll take 40% off, then that means you're now responsible for just 60%. And that makes sense because if you take 1 and you subtract 0.40, look at what you get, 0.6 or 60%. So hopefully that concept makes a lot of sense. Good. So for this next section and how we're going to end our class today is we are just going to practice establishing a relationship. That's it. We're not solving, we're not doing anything like that. We're just setting up our relationship. And I want to teach you how I like to go about doing this. Number 11, we have Ben makes $20 more than twice the amount John makes. So immediately when I see this phrase, I realize that I have two individuals, Ben and John, where we're trying to figure out the quantities for each of them. Okay, Doc, that's awesome. Ben and John, those are our characters for number 11. Now we're told that Ben makes, so we're here, Ben makes, right? That makes, it sounds weird because you're thinking it's an equals. Well, we're describing Ben, so Ben makes should be that same kind of expression, right? So Ben makes $20, we're not done reading, more than, we're not done reading, twice the amount John makes. So twice the amount John makes. So I'm going to say the amount John makes is J because that's John. Oh, I just said it. J is John. And that's our relationship. Notice that one of our characters is the independent variable itself, right? Or himself in this case. John is J. The expression we write for Ben is in terms of J, right? So that's how we write out their relationship. This is how they relate to one another. So if John has, let's say, $10, then Ben has 20 more than twice $10, right? So if we did the math, twice $10 is $20, so 20 plus 20 is 40. So if John has $10, Ben has 40, according to this expression. Let's do it again. Let's say John has $30. If John has $30, then Ben has 20 plus 2 times 30, right? 2 times 30 is 60 plus 20 is 80. So if John has $30, Ben has 80. That's essentially how we look at this relationship. Number 12. One number is 11 less than 3 times another number. So I like to use the exact language in the word problem whenever possible. One number, another number. So one number is, so we're right here. One number is 11 less than, less than means write it in reverse order. So 11 less than, you see how I'm writing in reverse order? 11 less than 3 times another number. 3 times another number. So I'm going to say that another number is just the variable itself, A. So 11 less than 3 times another number, which means another number is just A. Do you see how one of these characters is always going to be the independent variable itself? Okay? Excellent. The really cool thing about this is we are not establishing we're not writing out any equations, we're just establishing that relationship. 13 is interesting. Violet has $6,300 in a bank, part in a savings account and the rest in a checking account. So notice for 13, we're definitely referring to savings and checking. Now here's the interesting piece. All we're told is that Violet has $6,300 in the bank, and we just know that part of it is in the savings and the rest is in the checking. Well, what part of it is in the savings? We don't know. So what if I said that the amount of money in the savings account is S? Because we don't know it. But then how do I write the checking if I know that there's a total of $6,300? Well, let's think about this logically. If, for instance, Violet has $1,000 in savings and she has $6,300 total, then that means the checking would be $5,300, right? So if she has $1,000 in saving, she must have $5,300 in checking. But how did we get $5,300? Well, let's hold on that thought. Let's say she has $4,000 in savings. If she has $4,000 in savings, well, then she has $2,300 in checking. How did we get that? Because we know that if she has a total of $6,300, whatever she has in her savings has to be subtracted from the $6,300 to show what is left over. Yes, Kayla, you're exactly correct. Notice we're subtracting from the total. So total minus amount. Welcome back, Doc. So again, we could play around with this. If she has $100 in savings, 6,300 minus 100 is 6,200. Check. If she has $1 in savings, 6,300 minus $1, $6,299. Check. So every time we test this, it should make sense. That's how you want to work through these relationships. You want to just do a quick test to make sure that the relationship, according to the word problem, makes sense. All right. On your own, I would like you to take these two problems with you and then bring those solutions tomorrow. Type them into the chat first thing, okay? And that'll be how we do attendance. So 14, Ariel and Sarah share $450. And then 15, Ethan weighs 12 pounds more than 8 times as much as his baby brother Robbie. Beautiful. No fractions in either of these. Keep that in mind, no fractions in either. Just think about setting that relationship up. Excellent work. That was so awesome. You are all doing amazingly well. I feel like this chapter is going to be like a no big deal at all. And typically it tends to be a big deal because it's word problems. But you're all catching on so quickly. It is beautiful. Again, do 14 and 15 at home. Bring those with you to tomorrow's class. When you come to check in, go ahead and type in your answers into the chat. That will serve as the attendance that I take. All right. On that note, wonderful, wonderful job. I hope today's class was enjoyable for you and that everything made sense. And I look forward to continuing this with you tomorrow. Bye, everyone.